This is the Cycle World Podcast. Welcome back if you're a listener already, and welcome to any new listeners if you're new. We got more than 30 episodes behind us, so go check them out. We try to hit a wide variety of topics, from classic epic motorcycles like GSXRs and R1s and why Harley sold millions of motorcycles, to pretty far out stuff like what are the great books of motorcycling and combustion and stuff like that. For some reason, you guys love the TZ750 podcast. We're thinking about a whole TZ750 channel. Just kidding. Today, it's another sort of fundamental or theoretical a little bit, but it's also quite real, and that is heat management. How do you manage the heat in your motorcycle? How do we keep them cool enough, keep them hot enough, do all the things that make the motorcycle perform in the way we want it to? And really, when I think about heat, I think, well, it's quite relative. We think about the universe and we think about the sun. Well, the sun's pretty hot. The sun is very, very hot. We're talking about on Earth a small little window of heat management that works in our beautiful temperature range that we love and enjoy. And when it gets really cold, apparently the molecules stop moving. We've never tried that. I haven't anyway. But yeah, heat management, from engines to brakes, all of that. Of course, the principal problem is combustion heat. And I think that's a great place to launch.
Sure. And of course, that's where the desperation of the early engine builders rose, because although metal parts have a really high melting point, particularly iron, if you keep putting heat into metal, which an internal combustion engine does, every time the spark fires the charge, its temperature jumps up 2,600 K, and some of that heat is transmitted directly into the material of the combustion chamber inner surface and the piston crown. If that heat is not removed as fast as it is gained, the temperature of the parts will rise until pieces lose their strength and fail.
Creep.
So, yes. So some of the early engine builders I remember reading that Glenn Curtis asked about one of his early engines. He said it's the greatest engine in the world for about 3 minutes because it soon got hot and wouldn't do no more. So the heat has to be taken away somehow. And in the early days, a direct way of doing that was to surround the cylinder with the jug and keep water in it. And when the engine got hot enough, the water began to steam. And for every gram of water that was boiled away, it took 540 calories of energy. So those early farm engines that sit there going pack, 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 chop, 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 pack, 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 chop, chop.
Don't you just want to collect stationary engines? I do. I just want to go kapang, 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 and run a pump. I don't know, whatever.
Circulating water. Yep. And you presumably had some lad who was charged with pouring some more water in when it began to show signs of distress.
Well, it reminds me of an engine that was used in British motorcycles. There was one called a Matador. It was sort of circa 1907 or 1903. Way back, it was called a Bradshaw oil boiler. Now,
oil boiler, wonderful, yes.
How would it have gotten that name? Can't get rid of that heat. Yeah.
Granville Bradshaw, genius or charlatan, but he was in the game. So people began to put so-called secondary surface onto the cylinder head and the cylinder. Secondary surface, we call it fins. It's just a way of adding more surface area to parts that cannot rid themselves of heat fast enough through their own natural surface area. So we're putting very intense heat from combustion into the inside of the combustion chamber, so we're going to have to take extraordinary measures to pull that heat out from the outside surface and transmit it to the merry little breezes that are blowing through our lab or other enterprise. So cooling fins became a way you could tell an engine's point in time, because they kept getting deeper and more numerous. And when overhead valves came to be, the rocker boxes were mounted above the cylinder head on little standoffs, allowing cooling air to pass over fore and aft oriented fins on the cylinder head without obstruction. And
well, I just cornered our shop guy and tester and Evan Allen recently about cooling and about 90-degree cams or 120-degree, included angle, and tipping it forward to get all that air. We'd like them a lot closer, but it gets too hot on a race engine. So like the Gileras and all those with the really wide cam boxes for the same reason as the standoffs.
Yes, absolutely. And when Mr. Shorichiro Irimadri was asked about why the cam boxes on early Honda racers were so far apart, he said, because it allows you to place cooling fins directly over the hot combustion chamber. Now, we know that those deep hemi-combustion chambers were much admired in the early days, when a 6-to-1 compression ratio meant that you had a flat-top piston with a hemisphere chamber above it. And that worked acceptably. But as compression rose, the easy way to get more compression was to put a similar dome on the piston. And then people began to take thought about this. Well, the surface area of a true hemisphere is double that of a flat disc of the same diameter. We've built a heat trap here. And the taller the piston domes became, the more piston clearance was required, because it made the pistons run hotter. So the place where you could see the growth of cylinder cooling fins best was in aircraft engines, air-cooled ones. And they started out with a sort of a sprinkling of fins, the way some people put salt on their food, hardly at all. And they became more and more dense, so that for a long time they were maybe 1/3 of an inch apart. And then they became 1/4 of an inch apart. During World War II, BMW built its 801 radials with fins spaced 5 millimeters, 200 thousandths apart. That's about as close as they could cast them in those days. And they made them really deep. Also, there was the problem of material. The first cylinders for motorcycle engines, as well as for aircraft engines, was cast iron. Cast iron heads, cast iron cylinders. But if you put a bunch of rods of different materials with their inner end on the gas ring radiating out, you'll find that a copper rod gets really hot, even at the far end. But a cast iron rod takes forever to get even warm at the end. And you can imagine that a warm rod doesn't lose heat as fast as a very hot one. So it became important at a point to improve the cooling by changing the cylinder and head material. They switched from cast iron to bronze. And you will see references to bronze-headed Vincent TT replicas, and variety companies make the bronze heads.
Pre-war Triumphs, like Speed Twins. There's a beautiful
transmitted
available
heat about twice as well as cast iron, so it was a step forward. Also, just as you could seat valves on cast iron, you didn't need a hard insert seat. You could do the same with bronze. But it didn't take long for the rise in horsepower of sports and racing engines to outrun the heat conductivity of bronze, and people began to play with aluminum, and they found that you couldn't seat valves on it very well, although it was done on occasion. And if you shrunk, screwed, or cast in place hard valve seat rings, they would come loose in service. And that's bad for motorcycling. So at one point, Velocet, somebody there was riffling through the digest of metal alloys, and oh, here's a new high hot strength aluminum. And it's not Y alloy, which is so difficult to cast. Let's try this. And shrunken seat rings stayed in this modified Y alloy, and called alloy 142, millions of aircraft engine cylinder heads were made out of it. And after the war was over, Harley-Davidson adopted it for the aluminum heads on the panhead bike. So this has been the progression from low heat conductivity but high practicality, iron wears like iron, to medium practicality, bronze. Well, it's a little bit better, but man, that stuff is heavy. And finally, aluminum, a little tricky. You have to take care. You can't just use melted down pots and pans, but it can be made to work. And it was. And in aircraft engines, the fin pitch kept on getting smaller and smaller. And the reason was they needed more and more cooling surface area as those engines were supercharged, turbocharged, squeezed in every way to get power from them. And finally, when they were machining the fins out of solid forgings, they got down to 0.132 inch fin pitch, and that's all she wrote. People who tried such close pitches on motorcycles found they cooled worse than fins pitched at a 1/4 inch. Why? Well, it takes more pressure to push air through those tiny fin spaces than it does through more generous fin spaces. On aircraft engines, the cylinder fins and the head fins were all baffled so that you could enter the fin space at the front, but nothing could escape out the sides. And the only way out of that fin space was a vertical, tapered vertical slot in the back of the cylinder that let the air out. It had to go all the way around, cool the whole thing, and then be dumped out the back of the nacelle. With a motorcycle, fortunately, there are obstacles to the continuous use of full throttle. There are things to bump into, and there are officers of public safety who are waiting to tax you for your enjoyment. So what happens with a motorcycle air-cooled engine is when you gas it, most of the heat is not immediately transferred to the fins and then dissipated to the air. It goes into making the cylinder head as a whole hotter. In other words, the mass of the cylinder head is a heat sink, just like you have in electronics. And so when Harley's great racing director, Dick O'Brien, was working with Pete Zylstra, his draftsman, on the XR750 aluminum engine, he said, I want an inch of goddamn aluminum on top of that cylinder head. And Zylstra, who knew that people were going to come back to him afterwards and say, why is this thing so heavy? Said, well, how about a 1/2 inch? So they settled at 3/4. But there's a lot of metal on top of the cylinder head. Now, there's more to this. I once had in my shop at the same time a head from an FZ750 Yamaha, which was liquid cooled, and a GS750 head 4-valve Suzuki head. So both were 4 valves. Both were aluminum. But the one that was really light was water-cooled. And water weighs only 1/3 as much as aluminum. So filling up the water jackets did not make the cylinder head weights all that more similar. So the reason for the weight in the air-cooled cylinder is that need for a heat sink. You gas it, cylinder head temperature goes up. Oh, there's a corner. Oh, there's a policeman. We slow down. And so duty cycle saves the air-cooled engine in motorcycling, or it did save it for a long time. But then at a point, the hottest parts of the cylinder head began to give trouble. The area around the valve seats, exhaust valve seats, is really hot because hot combustion gas, even though it's been expanded through the power stroke, goes rushing out through the valve at supersonic speed, scouring away any insulating boundary layer on the inside of the exhaust port so that the conditions for heat transfer in the exhaust port are excellent, even though the gas in the port is not as hot as combustion gas at peak pressure. So about half the heat energy taken up by the cylinder head comes from combustion in the combustion chamber, and the other half from the inside of the exhaust port, which is why you will find recent designs have the shortest possible exhaust port, and it's made as small as possible. The goals in this case are to reduce its surface area. Now, you may have noticed that some of the recent parallel twins no longer have tremendous bores and wee little short strokes. They're moving back towards square. Bore and stroke are equal. The reason for this is that in a world of concern over emissions and fuel consumption, you want to expose the minimum surface area to combustion, which means making the bore smaller. So that's what everyone has done.
I would like to
yes,
take that notion to an extreme and say, would not the perfect internal combustion chamber cylinder be coated in such a way as that no heat was transferred or minimal, very little heat was transferred? I mean, what we're trying to do is keep all the heat. Ideally, you would keep all the heat energy in the charge and not transfer much heat to the engine.
Absolutely. And the U.S. Army spent hundreds of millions trying to do exactly that with diesel engines. Why not do it in spark ignition engines? One of the speakers at an SAE small engine meeting, when grilled by attendees as to why he didn't use coatings on pistons, and he said, well, old Swain ain't going to like this much, but the reason is detonation. Now, detonation, or engine knock, is a form of combustion that can occur when the last parts of the charge to burn have a thermal history of their temperature just rising and rising and rising. And when it gets to be about 950 degrees Fahrenheit, it becomes chemically altered. It turns into a sensitive explosive, which can auto-ignite and then burn at supersonic speed.
Is that active radicals?
Yes, those OH minus active radicals are rattling around in there. Not to be confused with Marxists, mind you. They're another kind of active radical, but when the population of those guys rises to X level, then auto-ignition and supersonic combustion become possible. And that's the rattling or pinking or tinkling sound that you hear when you're lugging an engine at low RPM and large throttle. And that tinkling tells you please don't do that.
Let up. We're going to start dusting aluminum off the cylinder
or shift down.
Pinch some
And
rings.
racers used to, and in the words of Joe Craig, who was Norton's legendary racing engineer, he said, the racer has to live on detonation's doorstep because you want to push the compression as high as possible. You want to have ignition at the ideal point to reach peak pressure where you want it. And you want a best power mixture in the cylinder. And when the tuner used to be responsible for all of this, actually having to make decisions. Nowadays, we have the engine computer, we have the oxy sensor, we have all sorts of temperature and barometric pressure sensors, and it's like having a crew of engine tuners working just for you. It doesn't matter whether,
they're
whether your bike is it's winter or summer, spring or fall, high in the Himalayas or down in Death Valley. That system is going to deliver good, solid performance. But detonation was this horror which could arise when your engine ran too hot, when the compression ratio was too high, when the ignition was overly advanced. Anything that raised the temperature of those last bits of charge to burn out at the cylinder wall is likely to provoke abnormal combustion.
So could you just explain, we've explained this before, but normal combustion is not an explosion. Normally we say like, oh, it lights off and lights the charge. It's really controlled. And I think that's an important point to remember.
Sure
and
is.
That's, I mean, we're really trying to light a fire that has a flame front of a certain speed. Combustion happens faster in a compact chamber where essentially you're looking at a tiny little cookie, you squish, and you have a little kernel, and that lights off, and it lights off in a beautiful way, and the pressure rises what you want. And when you have a hemispherical chamber, much like this microphone, if you light the charge way over here, sorry, Spotifyers, but imagine lighting the charge on one side of a mountain, and the flame has to travel over the mountain to get to the rest of the chamber. So if you have a plug on the side or even on the top, it still has to go all the way down. Whereas if it's nice and compact and flat, and it's a nice straight line, it can happen very quickly. And that speaks to Norton ignition timing, 28 degrees of commando, 28 degrees of max advance. What that means is combustion happens fast, even at the highest load and the highest RPM. You don't have to light the fire 40 degrees before the angle of the crank gets to where you want the most pressure to make the most of it. It's what a beautifully complex, fun system. And having all those sensors talking and sniffing out and knowing everything that's going on, rather than Joe Craig building a structure in his mind over and over again and witnessing, or Irv Kanemoto, as you have told that story before, in the pits, warming up in the morning going, oh, we're going to have to switch to those other needles. Just hearing what it's burning like. He was the sensor, I mean, I'm sure that they had some, engine telemetry type things.
Well, that's the way our society streamlines itself. The wisdom of the ages is put into an ECU, and the tuners retire and sit on their porches and watch the sunset. And once that process has fully matured, we'll all be there on the porch watching the sunset. In the meantime, we have this podcast to do, and the thing is, Mark just talked a moment ago about heat leaving the combustion gas by being conducted into metal. That's a loss of power. So the longer that combustion gas is held in the chamber, that is, the longer combustion takes, the more heat is lost from the charge, and the less power is delivered to the rear wheel. So
it reminds me of an important point that you made about drag racing at the time, where they were switching from iron heads to aluminum heads, and that the iron headed cars actually had a lower ET for a while until we figured out how to take advantage of aluminum's advantages.
Sure.
because iron didn't conduct the heat out of the chamber as fast in this window of running
For a few seconds. Yeah.
for a few seconds, it worked fine, and then it had the rest of the afternoon to
To cool.
to cool off.
Until the next round, anyway.
Yeah.
So Mark had spoken of, why don't we insulate the piston crown with some material such as zirconium oxide? Zirc oxide for a long time was used as an insulation on turbine blades. And here, the argument that was given by the NASCAR team manager, which I gave in written form, calling it, oh no, not the blanket analogy again, works like this. We lie down on the bed, and soon we've chilled out. In fact, we're cold. I can't sleep. So I get a blanket, I get a comforter, and I pull it over me. The heat that is being emitted from my body heats the inside face of the comforter, but it doesn't heat the outside face very much because the comforter is an insulator. So now we turn that around and we put the comforter on top of the piston. And combustion gas is heating the outside of the layer of insulation. It gets very hot because the heat can't travel through the insulator. That's the principle of an insulator. It transmits heat poorly. A vacuum is a great insulator, hence the thermos bottle. So the outside of the coating becomes very hot. On the next intake stroke, that heat is heating the fresh charge so that not as much of it can enter the cylinder. It expands. And while the piston is rising on compression, the heat that's still in that outer layer of insulation is heating more. It's making detonation more likely. Oh, well, don't worry about it. We'll lower the compression 2 points. Look what it did to our lap time. Yeah, well, reality is tiresome that way. And so people began to use the coating more as a very thin coating. This was told to me by Don Tilley, who lived down there in Statesville, which is NASCAR land. He said, you put on a very thin coating of that, just like anodizing, and it sort of discourages the first chewings of detonation. So it gives you a little more margin against detonation. If you're tuning right onto detonation's doorstep, you're going to need some margin.
Which, what was Don Tilley running is the question. That for those who don't know, what was Don Tilley running?
Don Tilley was running 883 Harley V-twins.
And gigantic Buells and
all those things. He blew so many head gaskets in his Buell 1340s that he went to 1/2-inch cylinder studs. Now, those are getting to the point that they're more like bats than they are like studs. 1/2-inch, that's hefty stuff. He said, I think we got her this time. And I
imagine
heard
the clamping force to get
just
that.
Imagine the distortion. But when you hear one of them go, one of those bikes came past start finish one time at Daytona, and I heard this squeaking. It's just a kind of a eep. That's the engine farting.
Yeah.
That's the difficulty of forcing high peak pressure out through the gasket, blowing it. And so that's another piece of meaning with regard to life on detonation's doorstep. You have to go to the highest compression ratio that you can make reliable.
And he wasn't shedding heat with water cooling. That's the other point there is he's limited by his fins. And
now in the design and in the development of large air-cooled radial piston aircraft engine, how's that for an adjective string? People reasoned, well, the engine's not actually overheating, but the oil is so hot that we're starting to get scoring between the piston and the cylinder. So let's cool the oil. Benelli patented an oil cooler in 1933 because motorcycle engines had hot oil on race day.
Coking would
So,
happen.
yeah, coking, that's the decoking was a process by which you took the cylinder head off your motor every couple of months and scraped all that carbon out of there, because if you left it in there, it would retain heat and glow red, and any oxygen and fuel molecules who needed a minister to marry them would find it in the form of that
Yeah.
hot glowing
And
carbon deposit.
the British, up until they went out of business in the motorcycle business in the 70s, were really big fans of like, oh, it's time to take off the cylinder head for a decoke. Like it was, it was not as often as changing the oil, but it was darn frequent.
Yeah. So the whole business of trying to insulate piston crowns and combustion chambers was driven by the U.S. Army because they wanted to approach an ideal which they called the adiabatic engine. Adiabatic roughly means without heat transfer. You know that if you're going to compress air in an air compressor, the air compressor cylinder is hot. It's not as hot as in a combustion engine, but it gets good and hot when it's running. But ideal compression is what is called adiabatic. And so they thought to themselves, our diesel tank engines are, say, 38% efficient. And if we could increase that to 50% or 55%, the operational range of our tanks would be greater. And so they put a lot of money into trying to come up with piston materials, cylinder wall materials, and so forth that did not require cooling. Because if the closer heat transfer depends on the temperature difference between the hot object and the cooler coolant. And the closer those two come together, the less the heat transfer. So they reasoned, if we have this extremely hot piston, cylinder wall, and combustion chamber inner surface, we won't have nearly as much heat loss and we'll get this great effect. But they found that not very much air was going into the cylinder, because when it encountered all those hot parts, it expanded and not as much of it would fit. The charge density dropped.
What did you say? Life is tiresome in this way?
Yeah, that's right. You're trying to do good. You've got an idea that theoretically should work. But in practice, they found that it was so difficult to cram fresh air. Diesels take in nothing but air and the fuel is injected later. It was so hard to get the fresh air into the diesel, and it took so much work to compress it, the pistons, because the diesel compression ratio in a large engine is 16 or 17 to 1, that they were losing in compression work pretty much all that we were gaining by approaching the adiabatic ideal. So engine cooling is a compromise. We're going to cool it just enough that the parts can live through the experience, but we're not going to overcool it by throwing away the thermostat and running our engine so cold that not all the fuel vaporizes.
Yes.
This is something we used to encounter at the races. You'd gas up and air up and start the engine because your practice was next, and it wouldn't. And you knew that the volatile part of the gasoline was the only part that was vaporizing. The rest of it was sort of saying, okay, Sarge, show us how it's done. And so the mixture was too lean to ignite.
Well, heat influence on this is something, heat everywhere, heat working on your choked motorcycle, and you're putting extra fuel in there so that there's enough of the volatile to get it to start from cold.
Yep.
It starts, you immediately back, if you're on a choke motorcycle, immediately back the choke into a range that it's allowing it to run, the velocities are increasing, your throttle's still closed because you're just running fast idle. And say you're at 1800 RPM and you think, oh, this is pretty good. And you go to take off and you load the engine slightly and you open the throttle. And for the temperature, the pressure change in the intake tract goes from high vacuum pulling things apart and making vapor to close to atmosphere, and all the drops go back together and they don't light off, and you bog away.
You can light vapor, you can't light droplets.
And it's heat, it's all heat related.
Yeah. So when Suzuki set themselves the goal in the early 80s of building a 100 horsepower 750, they tried to accomplish it with air cooling, and they found, as we've just discussed, that there were some complications. So this project was under the direction of Etsuo Yokouchi, whose name you may very well have heard. He was the JSXR guy. He was involved with the RG500 two-stroke Grand Prix racer. He was one of Suzuki's main men for years. He had an engineer on staff whose name was Masahisa Kamiya, and Mr. Kamiya raised his hand at some point and he said, in the war, we found that aircraft engines using oil coolers got 1/3 of their cooling from the oil cooler. Because think of it, oil is lubricating all the moving parts. You have to have oil passing through the connecting rod bearings because the oil that's in there is only 1/1000th of an inch thick, and it will quickly boil away from friction if it isn't constantly replaced with fresh, filtered, cooled oil. And all through the valve train, the cam drive, the chain sprockets, all of that is generating heat, and the oil is picking that heat up. So let's just run it through an oil cooler, and everything will be hunky-dory. But Kamiya said, why don't we increase the circulation of oil enough that we can mostly cool the whole engine? We'll run big jets of oil down onto the tops of the combustion chambers, and instead of having to have two plumbing systems, one for water or engine coolant and another one for oil, we'll simplify casting problems. The outside of the engine will still have fins, and the inside will be entirely cooled by oil. And that was the genesis of the, Yamaha, of the Suzuki GSXR, which was oil-cooled until, 1992, I think. And it was very practical for a street bike because although oil has only about 40% of the heat capacity of water, water is a truly remarkable substance. If you use enough of it, you can get the cooling effect that you wanted. But what really hurt was in racing, as 100 horsepower turned into 120 horsepower and 140 horsepower, oil was falling behind as a coolant, and they were adding more and more coolers. I remember one race they had coolers underneath the rider's forearms. There were coolers everywhere, and that had no future. So they switched to liquid coolant, namely Prestone and water.
But what high performance motorcycle today doesn't have a piston oil cooling jet squirting at the bottom of the piston? Probably.
Absolutely. And so this is something that bothers the people who own classic motorcycles. They see modern motorcycles with the little short skirted pistons and all these things that are so attractive to us. We look at them and say, I yearn for this. Give me that thing. But if you put that type of piston into your classic Triumph BSA or Norton, how can they get their heat lose their heat to the cylinder wall, which is the only way that pistons are cooled in such engines, is by touching the cylinder wall, which is cooler. We hope it's cooler. And if it isn't good enough, then we get scoring up and down the cylinder wall. Oh dear, oil failure. So we're obliged in the modern to have lightweight pistons because it reduces vibration, or it reduces the amount of counterweighting or the amount of balance shaft that we have to use to smooth the thing out.
Or the piston acceleration.
Yes. Yes, because the lighter the piston, the more difficult it is to yank the wrist pin right
feet
out
per
of it.
second, your average piston speed is certainly important. You know, like if you're going to modify your WR250 and you want to bore and stroke it, as I have done the numbers on this piece of paper,
Hey.
You know, like I could add 3 millimeters of the stroke, and at 11,000, I could still be under 5,000 feet average. But if I throw a really heavy piston at there, I might lose the rod anyway, because it's not necessarily the average velocity. It's like coming to a complete stop and yanking it in the opposite direction.
The one reason that modern engines have such light pistons and get away with it is that they no longer need a thick dome to act as a heat path, carrying that combustion heat that's going in the top of the piston out to the cylinder wall. Yamaha went to a piston dome thickness of 11 millimeters when the FIM said no more leaded gasoline. And that meant you have to lower your compression ratio. Well, what if we could reduce the piston temperature? We'll make the piston really thick. Then they had to change the rod bearings as well. More rollers in there. So once again, reality is so tiresome. But we don't have anything.
Truly is.
What's the alternative?
Alternative? Nope.
So modern engines are able to use thin crown pistons that are extremely light and which have minimum contact with the cylinder wall, which is what you want for low friction, because they have oil cooling jets squirting up at the underside of the piston dome. And you will find them. Yes. Yep. You'll find them on Harley-Davidson Big Twins. And there's even a precedent among the Harley faithful in the form of Tom Sifton, who, when he had the traditional cylinder distortion problems with the racing flatheads of the time, he thought, well, aviation fellas use piston cooling oil jets now. I think I better give that a try. Lo and behold, it worked. Because evidently we all live in the same reality. Oil cooling works there, probably work here.
So when I think of spraying oil at the bottom of the cylinder, we're gaining a great benefit, but it's also contributing to something else, another heat generating phenomenon called windage. And so this is something you just don't think about, but the oil flinging around. My related story is rebuilding the transmission in my 1971 Triumph TR6 car. I measured all my synchro clearances, and I staked the bearing staked the bearing housing because the bearing was a little hogged out, and I didn't know about green Loctite. So I put a new bearing in and staked it, fit pretty good. And then I thought, man, I'd love to see what goes on inside there with this thing running. So in a Triumph, you can take off the tunnel. The tunnel is cardboard. I fiberglassed mine to make it so that I didn't die of asphyxiation from carbon monoxide poisoning. I made a good seal, but I took it off, and the transmission's there, and I left the top off, and all the gears are there, and I just stuck my finger in the selector, and I said, well, I'll stick it in third gear. So I stuck it in third gear, made sure that the selector was in a good position and it wouldn't move. It was on its detents, fired it up, let the clutch out. I had wrapped the transmission with saran wrap so that I had a window, and I'm like, I don't know what's going to happen, but there's a lot of oil in here. And I revved that thing up, and I could not believe the violence of what was going on, of oil flinging everywhere and churning through the gears. And I was like, holy cow. I was like, well, how come a transmission can leak out the top? Well, that's why it can leak out the top.
Leak out the top.
Because it's just flinging everywhere. And inside the engine with oil flipping around and mist and everything. And every time a part contacts oil in space, it's making heat in the combustion or in the crankcase.
Here comes the pitch, a blob of oil.
Yeah,
Click, you hear it connect.
And windage and oil control inside has had some very exotic solutions. Screens.
It got really worse for those big twins with the giant round flywheels, Harleys and Indians. And Dick O'Brien, that former Harley racing manager, said that they called it wet sumping or just sumping, which meant that instead of the scavenge pump picking up oil as it was flung off from the bearings and returning it to the oil tank, it was somehow accumulating until the close-fitting flywheels picked it up and it was dragged through the small clearance between the OD and the faces of the flywheels and the inside of the crankcase, which means it turned into a high RPM viscosity measuring apparatus. And O'Brien told me, he said, you could see it at Daytona. He said, it was like a big invisible hand came down and said, no, you don't, because the motorcycle would just, and so he said, we had many innings of struggle to overcome that. And when Kawasaki in mid-70s designed its KR250 road racer, it was a tandem twin. It had two crankshafts that were geared together, and it did not...
Sounds like trouble.
Yeah, it did not have it wasn't built on a production model. So there was no kickstart. There was no extra bulge in the crankcase where the kickstart fit. Well, in prototype running, those engines had black paint on the magnesium crankcase. They burnt the paint off the gearbox, off the crankcase. Well, the two cranks were joined together by 4-inch gears, and the meshing speed was 12,000 feet per minute. And the classic idea of how to lubricate a gearbox is to fill it up to the shaft center line. So what was happening was that many horsepower, and each horsepower is 746 watts, many horsepower was being transferred to the oil and then to the inside of the cases, which got so hot that they burnt the paint off. So their idea was to do what RD 350 racers since time immemorial have done. Go out for first practice with 1,700 cc's in the gearbox because you want oil to be splashed everywhere if it's a fresh build. Then after first practice, drain it out, replace and rewire the drain plug, and put a cord in. And that made the problem less severe. And I thought I should build a little weir around the phasing gears in my KR250, and I drilled a 1 millimeter hole in the bottom to let oil in. And it just enough would be filling up all the time that the tips of the gear teeth would touch that and fling it about. But ideally, ultra-high-speed gearing should be lubricated with air oil mist. And short of that, a small oil jet into each mesh. And that's just what you'll find on Kevin Schwantz's RG-based Suzuki racers. You look at the top of the gearbox and you'll see a ridge going across right to left, and they're plugged, 6 plugged holes there. The drill went through, and then the tops where the drill came in were plugged. So now that oil gallery has 6 jets, one for each mesh. And you'll notice that many bikes have limited access to the primary gears. The gear oil, or the engine oil can't reach the primary gears in large volume because they will just chew up horsepower like you wouldn't believe. So ideally, we'd like to have just this little piddly stream of oil going in there. That's all those things need.
Strategic lubrication, oil jets on the piston, strategic cooling. You would talk to me about the story of like, well, some water is good for water cooling. Let's make these water jackets huge and it'll work great. And in fact, there was no turbulence. There was nothing to take the water away from the heat source. And so when they made them compact and you were forcing water through, it tumbled around and it took
picked
a
up
lot
heat
more.
Much better.
You talked
Yes,
about
you want turbulent flow because if you have laminar flow, it means that the layer of water slowly drifting along the hot surface is not being replaced by cooler water from in the middle of the flow. So that thin layer gets very hot and cooling decreases because it decreases the temperature difference between the hot thing and the cool coolant. So early engines had these great big water jackets. They soon learned better. Oh, we need velocity in there. And, well, maybe velocity isn't the end of the story either. So they made water jackets with plexiglass windows so that they could look in and, oh, look, nothing's happening here. Just whirling around in one place. So a lot of work goes into making a successful water cooling system. It's a lot more than just surrounding the hot parts with basically a pot of water.
Well, I observed turbulence in college with a friend of mine who was disappointed by the warmth of his unopened beer. And he went to the cooler and stuck it in there and constantly rotated it.
Yeah.
So that it would cool faster and he can enjoy his
You bet. And of course,
crispy cool beverage.
We all know intuitively the boundary layer because you run a hot bath and you think, man, that's going to be comfortable. What'll I read? And got the bath ready. Yeah, that's almost too hot. Just what I want. And I put my cold self into it. And you lower yourself into the water and you're delighted for about 3 minutes. And then you feel something's happened here. I don't feel good anymore. So you stir around a little bit and now you feel better. Oh, okay. Now that's how it's supposed to be. Well, what's happened is there's very little water velocity in the bathtub. And the water next to your skin, from colliding with your cooler skin, loses energy and forms a stagnant, cool layer, which is no longer heating your skin, and now you're pretty unhappy about it. So finally, you have to turn on the hot water and paddle furiously to get that hot water in contact with yourself. Well, any vehicle that is moving through the air, an artillery shell or an airplane or what have you, this boundary layer gets thicker and thicker the farther the flow travels along the surface. And it's a very simple thing. And the fact is that air molecules colliding with the less energetic, or actually, it depends on whether you're traveling with the vehicle or standing next to it. But there's an energy exchange which causes the vehicle to drag a layer of air along with it. And it moves very slowly. And it was said that on the great Zeppelins, that there was a hatch, a companionway with a hatch at the top, where you could emerge at the top of the aft end of the gas envelope and have a look around. And it was like the thing's going 60 miles an hour and you don't feel a thing because you're in the boundary layer. The thing is 750 feet long. So it can accumulate a hell of a boundary layer.
Yep.
And that's also why when you see a P-51 Mustang, the intake to the cooler, which is under the fuselage and just behind the pilot, there's a gap between the entry and the bottom of the fuselage. That is there so that none of that slow-moving boundary layer is going to go into the cooler and be wasted because it doesn't have the energy to carry its weight. You want full ram air pressure, not low energy, feeble boundary layer. So you'll see those gaps on a lot of vehicles that are trying to scoop high energy air.
It sounds like the reason we have jets in hot tubs as well.
You got it. Absolutely. That's why a hot tub has those jets, because the water temperature, once you get it right, those jets are going to see to it that that boundary layer is scoured away, just like I talked about the boundary layer in the exhaust port being scoured away by the sonic flow. Boundary layer is scoured away. Temperature difference between your skin and the warming liquid is high, and so is your delight.
A delight, indeed.
But there are all sorts of things that require dealing with heat. For example, brakes. It used to be when drum brakes were nearing their end that the drum would expand. Kawasaki had some experience with magnesium drums. The drum would expand and the spokes would get loose, and the rider would say, "This thing handles like poo-poo." And then the team manager would come over and say, "Nothing wrong with it. Spokes are all tight. Everything's fine. Get out there and do your job." And so the problem with drum brakes was that you're putting heat into this ring of material, which is restrained on one side by the structure of the wheel. And so the ring is going to open up like in a sort of bell mouth fashion, and pressure from the brake shoes is going to be more like edge contact. So they came up with disc brakes. The disc can't get away. There's a pad on either side.
Well, I had a 1964 Cadillac with four-wheel disc brakes, and it was really great for two stops, for two aggressive stops, and then I always described it as brake fade while you wait. It's just
while you wait.
You'd put it down, and then it would get worse as the heat, just had nowhere to go, and everything did. They were great big drums. They must have weighed 25 pounds each.
Yeah,
huge finned iron drums, and they were it was a beautiful braking system. And obviously, we're not braking at the end of the Mulsanne straight, and we're not doing that over and over again in a '64 Cadillac. So,
but in the late 30s, the German Grand Prix cars, the Auto Union and Mercedes, they had enormous aluminum drum brakes, very large in diameter, and the drivers took it for granted that at about 30% race distance, you would have to start using downshifting for more and more of your slowing down for corners, because the brakes were sort of saying, "Well, I did all I can, and I'd love to help you, but that's how it is."
Yeah, that expansion of material, the early kind of the fixed mount discs. Going cone shaped. I always thought about RDs. I came to your shop years ago with the RD 350.
Yeah.
And you were porting away, and I'm working, chasing threads and doing all that. And I'm looking at the cylinders, and there's gaps in the fins all the way around. And there's no reason for the gaps except to say I bet that's where it cracked, because the depth of the fin is, inches. Yeah. And so, it's not going to.
They interrupt the fins so that the hoop,
you don't have a ring.
No, the inside is closer to the heat, so it's expanding more. The outside of the fins is cooler, so it's expanding less. So it's going to crack. So let's make gaps there.
Factory cracks.
Take care of that. Well, in '78 at Loudon, we had this terrible problem with the TZ750 that Rich Schlachter was riding. Something was pushing the brake pads back. He came in and he's gesturing and showing the brake lever coming to the bar, and I got out my 12-inch straight edge that I carried, and slapped it onto the disc, and there was a gap. the disc was cone-shaped. Well, it was flat when it was installed, so how did it become cone-shaped? What it turns out is the brake pads on those Yamahas were about 2 inches in diameter. So the outer part of the friction track was experiencing high horsepower friction because the velocity was high, and the inside of the friction track, lower horsepower, lower velocity of force times distance. So the outside of the disc was becoming very hot, and as it expanded, the inside of the disc elastically resisted that until it reached its elastic limit, and then it yielded. The outside of the disc physically stretched the inside to a larger diameter. Then when the disc cooled, the inside was too big for the outside, and the only thing it could do was to pop into a cone shape.
And so we got floating discs, so they weren't anchored by firm bolts at their centers to hold them in place. And then what do? We made the friction area short,
narrow yes,
from top to bottom,
so that the velocity, friction, rubbing velocity was not so different between the ID and the OD of the friction track. And what I did that night, I rushed home in my silly old 6-cylinder van, getting 17 miles per gallon, and I cut radial slots in the discs, and I terminated them in drilled holes so that there was a radius at the tip of each saw cut. Now, don't try this at home, because if you're like me, you worry to yourself, I've shown this disc a crack. What if it likes it? What if it propagates it inward until pieces come off? Well, all kinds of military aircraft have brakes that have separate segments to their brake rotors. So there's a tremendous clattering when they're taxiing. All these separate pieces. Anyway, it worked. The next morning, when I made the saw cuts, the disc flattened out very satisfactorily. And the next morning, first practice, no brake troubles. This is so wonderful because in racing, so many things that you try just don't work. The race bike looks back at you like, did you want something? What are you trying now? And the rider comes in and says, well, maybe it was a little better. And he's being polite. But this was a case of something that actually worked, and I was delighted.
Such a good feeling. Such a good feeling. Yeah.
So the permanent solution, of course, was to make the friction track narrower and to make the disc mounted in floating fashion on the carrier so that it could expand however it liked, and without being hotter at the outer edge, cooler at the inner edge, to such an extent that it worked. So that was on another occasion. This is for the people who believe that they can gain 8 horsepower by replacing all their ball bearings with ceramics. We had a cast iron disc on the back of a big Kawasaki, and it was mounted to the hub. And the rider went out and melted all the grease out of the wheel bearings with that brake. Melted it all out. Gone. Now, normally, wheel bearings don't get hot enough to melt all their grease out, so I conclude that each wheel bearing is not consuming 1 horsepower. Undoubtedly, it's consuming something because the bearings get warm. But 746 watts? Don't think so. Anyway, I made an insulating mount for the brake disc, and the grease stayed in the wheel bearings. And the modern motorcycle is the result of all these little steps with people like myself who said, I've got to come up with something for tomorrow. And that business of the radial slots, I took that from Norton clutch plates that I'd seen that had radial slots in them for the same reason. You'll notice, by the way, that clutch plates, some of you haven't ever seen a clutch plate, I'm sure, because this is the new century. But clutch plates, the friction surface is radially very small. It's just a narrow track. And that is done for the very same reason that I just described, causing the coning of brake discs. So every time that energy changes form, a tax is imposed on it, and it usually is paid in the form of heat. And that was the case with brake disc failures. In the case of rear suspension units, there was a mad craze for making everything possible out of aluminum. And what happened was unwanted suspension energy is turned into heat as the damper piston forces oil back and forth through small orifices. Result, the damper fluid gets hotter and hotter. The body of the damper becomes hotter and hotter. Oh, a gap has appeared between the piston and its bore. The damping has gone away. Bumpity bump. So people designing suspension dampers took steps to make sure that whatever form of seal was made between the piston and the cylinder, damper getting hot didn't leak. So any place you look, you'll find this tax being imposed on transformations of energy. Oh, I'm charging my laptop. That's very comfortable. I'd like to have that on my lap. It's like having a pet cat. There is the charge-discharge efficiency, which can be as low as 70%. You're putting energy into the battery to charge it, but you're having to overcome electrical resistance in the various elements of the battery, and that resistance is turning the flow of current partly into heat. So
there you have
once
it, folks.
again,
Death and taxes.
Reality has to be dealt with. And the motorcycle is the reason that I was originally very interested in racing cars. And I turned to motorcycles because they were in my scale and within my financial reach. And I think that's true of a lot of people. And I think the motorcycle is a marvelous study in so many different subjects. And I've enjoyed that all my life.
Same.
Yeah.
The dynamics, the working on them, the problem solving that problem and getting what you came for.
Yeah.
Or more of what you came for, really.
Yes, getting more.
More.
And of course, waste is offensive.
It is.
When Pratt & Whitney was developing their geared turbofan, an engine for large commercial aircraft, the fan provides most of the propulsion. And it has to turn slowly. But the power is coming from a turbine, which likes to turn much faster. So they usually compromise. They make the turbine very large so that the gas has more leverage with which to turn the shaft, which is turning at a lower speed to drive the fan. But both are losing efficiency. So they said, let's bite the bullet. We'll put a gearbox between the turbine and the fan, 3-to-1 ratio. And what they came up with was 13,000 horsepower going to drive the fan during takeoff. And the power loss in the reduction gear is 100 horsepower, or 0.7%. Very small loss. And I think that's wonderfully admirable. You know that the dyno people are always saying, well, there's a 15% loss between the crankshaft and the instrument in the office here. Well, that's vulgar. That's nasty. Primary gear, maybe 2%. Transmission gears, maybe another 2%. Chain, maybe another 2%. You know what I think? That 15% loss comes from tightly strapping down the back wheel of the motorcycle onto the roller. There's so much rubber flexing going on. Most of that power loss is back there.
We'll have a look at that. We don't overly tighten down our bikes on the Sucker World dyno. We dyno almost everything that comes through. We're consistent about what the tire pressure is.
And yeah, you have to be, because that's working with instruments.
And we strap it down, I want to say, just right, because we're doing a chassis dyno, we can't have slip. So we have to balance slip versus overdoing it.
Yeah. So in that, there's another one, which was when the British rubber industry began applying the wartime discovery of synthetic rubber to automobile tires. They found that butadiene styrene rubber could, if it were in the proper mixing ratio, give extraordinary grip, especially wet grip, but also increased dry grip, such that when they made race tires for cars out of it, the race car lost several miles per hour in top speed because that type of rubber has a lot of internal friction. That internal friction was acting to produce greater grip through the corners so that the lap times improved by seconds. So once again, you have to make a deal with Mother Nature in order to get what you want. Yeah, we like impressive top speeds, but we also want to be ahead at the end. So we're going to go for lap times. Yeah.
Well, thank you for listening, folks. We really appreciate it. This episode is graciously brought to you by Octane Lending, our parent company. We have a link in the description here that will take you to the Octane Prequal Flex, it's called. You can shop. We do trailers. Obviously, we're here for motorcycles, but you can look at all kinds of different things in the power sports realm, jet skis or, watercraft and all those. You shop around, find your bike, find out what kind of loan you could get, et cetera. So we appreciate the sponsorship. Again, we wouldn't be here without them helping us out. We appreciate that a lot. We hope we have contributed to the terrible signal to noise ratio found on the internet. Sometimes we hope we've delivered an hour plus of something worth listening to. We appreciate you being here, longtime listeners. And if you've made it this far, new listeners, we appreciate that as well. Get in the comments. This discussion and one that's forthcoming about fuel types and so forth have come from the comments in our podcast. And anyway, we love hearing from you and carrying on that conversation there. So thanks again for listening, everyone. We'll see you next week.